All right, we're going to talk about projectiles today. I have a standard definition for a projectile, but it's a complete lie. And if I might have gotten to this point yesterday, but you guys, I don't think I did, so I'm going to act like I'm starting fresh, but I'm going to tell you the lie anyways. A projectile is an object that is moving in 2 or more dimensions, but experiencing an acceleration in only one of those dimensions. Do I have to repeat that 3 times for you to write down the lie? All right, 1 time is good, or 2 times? 2 times. A projectile is an object that travels in 2 or more dimensions, which means 2 or 3, because they all travel in 4 dimensions, but let's just say 2 or 3 dimensions, but experiences an acceleration in only 1. It's an out-and-out lie, but it works for basic high school discussions, because what it's saying is, and let me just be, kind of not precise, but let me just get something to demonstrate with. It's saying that we have an object that's being launched in such a way that it's going to travel in 2 dimensions. So something like this, where I'm launching an object and it has a velocity that is at an angle. Now, if there were no gravity, this object would travel in 1 dimension, right? Just along that arrow. But if gravity is acting, and by the way I'm drawing this, you guys can kind of see it, but let's just make it obvious. If gravity is acting this way, well, then the object's path is going to curve, and it's going to travel in 2 dimensions because of that. Does that make sense? Now, what we're saying is this object travels in 2 dimensions, but experiences an acceleration in only 1 of those dimensions, and therefore the object travels in kind of a curved path like so. Now, the truth of what I want you to have in your notes is a projectile problem is a problem in which an object traveling in 2 dimensions can be studied by breaking it into 2 one-dimensional problems. That's really what I want you to know. Because I don't want them to switch this up on the exam and have you confused, because they could. So let's ignore the real rules of the real world for just a minute and state that we could have a problem in which you have an object traveling in 2 dimensions, but it can be studied by breaking it up into 2 one-dimensional problems. This one is like that. There are 2 one-dimensional problems here. There's the fact that the object is traveling with a velocity that is horizontal, and it's traveling with a velocity that is vertical. It has 2 velocities at the time of launch, right? And I should say it this way. It has 2 components to its velocity at the time of launch. One aligned horizontally and one aligned with gravity. This component of the velocity experiences an acceleration due to gravity and will therefore change. But this component of the velocity does not experience the acceleration of gravity and therefore does not change. If I break this problem up into 2 parts, a part that studies the horizontal velocity and a part that studies the vertical velocity, I can make predictions about this object's motion. Does that make sense? 2 one-dimensional problems. They're both about the projectile, and they both can help me figure out how long it stays in the air, when it hits the ground, stuff like that. But note, I can study these independently. This portion of the velocity is a constant. And this part of the velocity is all that accelerated motion stuff. That's what I mean by we can break this problem up into 2 one-dimensional problems. But don't get stuck on that conversation, because what if I have a fake problem where the wind is blowing this way and causing a horizontal acceleration and a vertical acceleration? I can still break this problem up into 2 one-dimensional problems. The thing is, and this is what should be in your notes, I said this a month ago, but it's been a long time. We can only do one-dimensional problems. That was one thing I said. The second thing I said is, to study uniform accelerated motion, we can only deal with 1 acceleration at a time. So, if I can break my problem up into 2 one-dimensional problems and study them separately, then I can do the problem. Now, part of the reason I'm making this statement is because I have people in the room who are in E&M. And it is possible to have an object traveling in an electric field and a gravitational field. And under those circumstances, there'd be two accelerations. There are projectile problems on the E&M exam that do this. There are projectiles that are just accelerating in two directions. But, and I mean this with all sincerity, there is the real world. The real world has air resistance. Air resistance presents a problem where you cannot do this, because air resistance provides an acceleration that opposes the direction of motion. So I've drew the arrow opposite the direction the ball's moving, right? So as the ball moves, do you notice that the acceleration will be changing direction all the time? And do you notice that not only is it changing direction, but it would be changing size because it's based on how fast the ball is moving. And I bet you would agree that the ball's speed is always changing in something like this. This problem cannot be done using the tools I'm going to teach you for projectile motion, because it cannot be broken up into two independent one-dimensional problems. This requires something different. Okay? So I'm trying to give you the big picture, because the thing that AP is famous for, and the thing that I want you to be, is adaptable. We can do this problem that I'm going to describe in a minute because we can break the problem up into two independent one-dimensional problems. And that's the one I want to talk about today. So that's kind of the one I have drawn here. So I'm going to stick with this picture for the remainder of our open conversation. First, consider a couple of things about this. This is symbology. So let's go with some symbology. We generally define these problems based on the launch velocity, which I will use V0 as the launch velocity. However, the launch velocity is usually provided in some relative form. The relative part of the launch velocity is the angle. They are stating what they want you to use as a coordinate system by giving you an angle at launch. Almost always, the angle at launch is relative to the horizon. So because of that, the angle will be something like measured, here. So you'll be given a launch velocity and a launch angle. And the angle is almost always related to the horizon. Because of that, we will generally call the horizontal direction the x direction. And I will label the component of velocity that is in the x direction Vx. Vx does not experience an acceleration and therefore is constant during the object's motion. Vx does not change as the object goes from launch to landing. Vx stays the same the whole time. Vx is a constant. I'm waiting because I think everybody needs to commit that somewhere. At the same time, there is a component of the velocity in the y direction, which I will dub Vy naught. The horizontal one doesn't get the naught. The vertical one does, because this one changes. It only has this vertical velocity at launch, but it's being acted on by gravity. It is accelerating, so this velocity will change the entire time and only has this velocity at the launch of the object. Now, you sharp cookies out there realize that Vy naught, V naught, and Vx are all related. But because I'm supposed to be very clear, now I want you to think about this for a moment. The object itself travels along this curved path. Eventually I'll prove some things about the path, but the thing I want you to be keeping in mind is that while it's traveling along this curved path, the horizontal velocity is constant. Boy, I've said that a couple times now. And I'm trying to drive it home so that you understand that no matter at what point we talk about this, the horizontal velocity is going to stay the same the whole time. But that vertical velocity isn't. Gravity's acting on it, so after it's started to go upwards, the moment it leaves the launch site, it's going to be slowing down. And then, of course, it will eventually stop, turn around, and begin coming down the other direction. And, as it gets closer to the ground, it's probably going to have pretty good speed. Be aware, though, the object has one velocity. These are components. The whole time we're observing the object, it has a single velocity that is the result of the components. So you are tracking the components of the object's velocity, but the object has one velocity. At any time, they could ask you, what is the velocity of the object? And you would have to use the components to figure out how fast it's going. There will be other methods to do that, but right now, that's what you have at your disposal. Are we doing all right so far? We call the point where the object lands the range of the projectile. Now, a projectile motion problem is just a motion problem that requires a little more consideration. So, for the time being, I want to give you a strategy to solve projectile motion problems. And that strategy involves a template. I want you to follow my template, please. It's not a big deal. It's just a way for you to organize the information that you're going to be given. I want you to compartmentalize the problem. I want you to recognize that there's going to be a horizontal portion of your problem and a vertical portion of your problem. And every time you start one of these problems, I want you to consider that the vertical portion of the problem is going to have all the variables you've come to associate with accelerated motion. I'm just categorizing them now for the y direction. So instead of delta x, I have delta y, because we're talking about up and down. Instead of v naught, vy naught. Instead of v, vy. So all your motion equations, they're right there. At the same time, this generally refers to gravity. Doesn't have to be the gravity on the Earth, could be the gravity on the Moon, gravity on Mars, doesn't matter, but generally refers to gravity. We just talked about the fact that we could probably write this in terms of the launch velocity. You don't have to make it part of your template, but you could. At the same time, the object's moving sideways. So what would have been delta x, I'll likely call the range. But that's just a horizontal displacement. We're going to have Vx as well, but Vx is a constant. So there's no acceleration. So the only other thing that I would have to deal with here is time. And here's the thing about these problems. The time it takes the object to travel up and down is the same as the time it takes the object to travel side to side. To solve a projectile motion problem, you are usually linking the vertical part of the motion with the horizontal part of the motion through time. If you want to find out where it lands, you need to know how long it's in the air so you can figure out how far to the side it traveled. Now, from your work on uniform accelerated motion, you should remember that you need usually 3 pieces of information. Because you have 5 motion equations, as long as you have 3 pieces of information, you can usually solve for the 4th. And at the same time, there's no acceleration here. The range equals Vx times t. So you're going to need either 2 pieces on the right side or 3 pieces on the left side. Look, there are any number of variations and permutations on projectile problems. Some really challenging, some not so much. So let's do the basic problem. And when I say let's, I mean you. I don't think you need me to do this. I think you have all the skills necessary. So let's set up a basic projectile problem that you could successfully complete, all by your little selves. Let's say I have an object that's going to be launched with a launch velocity of 5 meters per second at an angle of inclination of 30 degrees. Let's say it's on a building that is 2 meters above the ground, or on a platform 2 meters above the ground. And I would like you to tell me, where does the projectile land on the ground below? Standard projectile motion problem. Now, half this room should go running now and get it done. However, I have a subset of you who need me to do something with you. So the subset, pay attention to me. I know who you are. But you guys who know what you're doing, go run. Do this problem. This is not tough. All right, subset, look, I know there's a lot to keep track of in these problems, so I'm going to repeat something that I think bears a little repeating. First, there's no difference between this problem and the other problems we've done. There's just more that you have to track. So I want you to start every problem by setting up a template to help you organize the information that is given. That's what I'm going to do, especially as we start getting permutations to these problems. Go through and put in this template what you've been given. Be careful. Some of the information given is going to refer to vertical information and some is going to refer to horizontal. No longer are you going to be easily able to look at the units of something and say, well, it's only going in one spot, right? There's 2 places where meters can go, 4 places where meters per second can go. So you got places here. Just focus. The object starts at the top of a 2-meter tall platform. It's going to land 2 meters below where it started. That's a change in y. So 2 meters goes there. I was given a velocity, but none of the velocities are in my template. I was given the launch velocity. So if I want to find the initial y velocity, I have to do trig. But I already know that's going to be 5 sine 30. Nowhere will I write just 5 by itself, because I want the components. While I'm dealing with velocity, I might as well deal with the fact that the horizontal velocity is going to be 5 cosine 30. Just get it in there. Always be cognizant of what you've been given. At the same time, it's being acted on by gravity, so I know I'm going to have an acceleration of 10 meters per second squared. All right, just like a motion problem, I go through, figure out what's been given. Do my best to put everything that's been given where it goes and to throw out any extraneous information. After I've done that, you understand that the next thing is probably the most important thing. And let me be clear to all of you, if you didn't do this already, because I said run off and do the problem on your own, then you're forgetting a cardinal part that I've been trying to say you should do for the last 5 weeks. Determine direction. Look, we're going to get into forces here real soon. And what you say is, oh, I forgot the negative sign. What I say is you forgot to consider reference and direction. It's a bigger problem. Become good at this. Make choosing direction a thing you do every time. Build it into every single problem. I'm choosing direction. I'm saying up is positive. That means the object landed 2 meters below where it started, so I have to make that negative. But it was fired upwards. I have to make that positive. But gravity is pulling it downwards. I have to make that negative. And it was fired to the side in the positive direction. I'm going to make that positive. And yeah, I know. You don't have to write positives in front of the numbers that are positive. Do you know the reason why I do that isn't because I need to see it? I do that because some of you get lost and you forget where you are and you don't know what to do next. If you see that you wrote a positive down, that should clue you in that you considered direction already. You can go to the next thing. Maybe you had to stop to check your TikToks and, or your Insta posts. And you went back, wow, where was I in this 20-minute long physics problem? Well, I at least determined direction. I know that. All right? Now, you need to figure out where it lands. The only way you can do that is by getting the time. You do not have enough information on the horizontal side to get time. But you have 3 pieces of information on the vertical side. You could use that to get time. That's your job. Figure out the time on the vertical side, use it on the horizontal side. And I want to be clear, all of those motion equations are the same motion equations now. They just have slightly different letters in there to put the y in place. So let me know I'm dealing with the vertical stuff. I can't tell if that's your hand or you're picking at your hair. So you either decide and commit to the question or don't. Go ahead.
I was wondering about the vertical component. to the range up to be positive and down to be negative, wouldn't that be plus 2 meters?
Is it landing 2 meters above where it started?
No.
Is it landing 2 meters below where it started? Right, it's a displacement, so it doesn't matter that it goes up first. It's only comparing its final position with its initial position, and it will be 2 meters below where it started. So that's why we say -2. Now, I have an aside here, because I'm looking at some of your faces, and some of you are lost, but pay attention to this point. -2 equals 1/2 times -10 t squared plus 5 times sine 30. It's 2.5, right? Because sine 30 is 1/2. Plus 2.5 t. Look, every projectile motion problem has the potential to be a quadratic. Get over yourselves and get this done fast. I'm done playing games with you guys when it comes to the simple math stuff. And some of you are committed to making this as hard as possible. You have 2 minutes to figure out how to do this on your calculator if you don't already know. I should walk around and see on your calculator that you can get the zeros. That, or you better be good at the quadratic formula and don't balk at it. I don't need the negative roots. This is time. Positive roots only. Be quick. If you don't know how to do it, call me over there. I'll help you. If you know how to do it, you make sure the person next to you knows how to do it. I'll be mad if I come to a table and find a whole table where everybody but one person doesn't know how to do it. Be good, be fast. Now look, I want to say this, and I want you, please, please, understand. There's lots of these little tiny steps, right? Every one of them just there in your way. It's math. It trips you up sometimes. Do you understand why I keep saying make the math effortless? Because you got lots of other things going on here. We can't make the math be the hard part. Your calculator will do this with a couple of keystrokes. Let it. If you can't, yeah, quadratic formula it out. That's fine. But how many minutes do you have in the AP exam to do this? Not enough for sure. And definitely not enough to be thinking about it. So 0.93, 0.93. Figure out my solution. Range equals Vx times t. This will be where it hits the ground. So 5 times cosine 30, got plugged that into your calculator, get 4.33 times 0.93. All right, so 4 meters. That's my range. It hits the ground 4 meters away from where it was launched. Be aware, this is the horizontal distance. That is not this distance, right? It's the horizontal distance, the distance along the ground. This is the basic problem. You understand there's a whole slew of other probable accessory things they could ask. Let's talk about some of those, okay? Most likely kinds of things that could be asked on these problems. How high does it go? That seems like a reasonable one, right? If you want to find out how high it goes, that's simply changing the parameters to say, I want to find out what the delta y is when Vy is 0. Max height will be attained when it's no longer traveling upwards. That's when Vy is 0. So you don't put in the 2 meters now. You're trying to figure out what delta y is. But be careful. This delta y will be how high above the 2 meter point. So you may need to add the 2 meters to that to get how high above the ground it is, right? Be thinking about the problem. I mean, draw a picture. That'll help. How about where along the ground? Where along the ground is it when it's at maximum height? Similar question, right? In this one, we're still going to set Vy equal to 0. This time we're going to solve for t. We will not put anything in for delta y. But we'll find the time, and then from here, find the range. There's lots of other things too. So let me make sure you understand that this is not an exhaustive list. But be aware, you could be asked to find the velocity when it lands. If you're asked to find the velocity when it lands, then you're probably being asked for two things, aren't you? The speed, which is probably going to be Vx squared plus Vy squared to the 1/2 power. Do you see what I'm trying to say? Because you're going to have the horizontal component and a vertical component. It's going to strike the ground over here, but it's going to have what you've been dubbing two components of velocity. And you'll have to figure out the actual speed. Do you guys see what I'm saying? But also, if it's asking for the velocity, then it will probably want you to figure out this angle too. Be careful which angle you solve for. If they gave you the launch angle relative to the horizontal, you have to provide them the landing angle relative to the horizontal. Okay? All right. That's thorough and explain things. I want to be about the relationship here, so let's draw this so it's very obvious and you can't escape it. If this is V naught and the horizon is this way, and that means that this is theta, then there is a Vx in this direction and a Vy naught in that direction. It should be clear to all present in the room that there is a relationship between Vy naught, V naught, and Vx. Do we see the relationship? Now, as long as our angle is always made relative to the horizon, it will be true that this will always be V naught sine theta, and this will always be V naught cosine theta. But it has to be that the angle is measured relative to the horizon. Be careful. By the way, this would be called an angle of inclination. It produces an upwards y velocity. Listen closely when you read a problem. If they say that the object has an angle of declination, they are secretly telling you that the object is going to have a y velocity that is going to be downwards at launch. This would be an angle of declination. Makes sense, right? A declining angle would be downwards, an inclining angle would be upwards. So please, just definitions. I don't do that. I will say the angle is downwards. I'll say below the horizon, but they can say inclination and declination. They haven't done that in years, which just means it's right for now. All good? Keep going? Good.